Welcome, my dear students. In the last class, we have discussed on the fundamental torque equation. So, this is the fundamental torque equation where Te or tau E is the electromagnetic torque. And TL is the load torque. Omega m is the motor speed. Theta, it is the angular displacement. J is the moment of inertia. So these are the general notations that are used in the fundamental torque equation, and the derivation that has been shown yesterday, and it is very important with respect to the dynamics of a machine. So now let us study this J d omega m dt. So now, how many cases are there? There are three possible cases. T is greater than TL, T is less than TL, and Te is equal to TL. So if, let us consider case number 1, this is number 2, this is number 3. Let us consider the first case where the electromagnetic torque is greater than the load torque. So that means if T is greater than TL, that means T minus TL, that is greater than 0. So that means what is T minus TL? It is J d omega m dt. That means J d omega m dt. This is greater than 0. That means d omega m dt is greater than 0. What is d omega m dt? This is the angular acceleration. That means alpha is greater than 0. That means I can say that the rotor is accelerating. The rotor is accelerating. Similarly, for the second case, if Te is less than TL, so that means this J d omega m dt, that should be less than 0. So alpha will be less than 0. That means the rotor of the machine or the drive, that is retarding. And the third case, when T equal to TL, that means this d omega m dt, that is equal to 0, or rather omega m is equal to constant. That means the rotor is moving at constant speed. The rotor is moving at constant speed. So now there may be two types of motion. One is the rotational motion and another is the translational motion. So angular motion means rotational motion, and linear motion means translational motion. So suppose there is a mass m and there is a wheel or a pulley, you can say like this, of radius r. So it is rotating in the clockwise direction like this. Similarly, this circular arrangement, it is also rotating in the clockwise direction. What is the angular speed? It is omega. So this part of the system and this part of the system, they are exhibiting rotational motion. But here, between them, a mass m is connected by a rope. So that means this you can say is due to motor M1, and this is due to motor M2. So this M1 and M2 are exhibiting circular motion, whereas this mass M, it is exhibiting linear motion. So the force exerted by this rotor, or this gear you can say, it is Fe in this particular direction, where the motor torque or the electromagnetic torque, it is Te1. So what will be the direction of the load torque? The direction of the load torque will be in this direction. So TL. So here also it is already given the direction of TL. It is in the anti-clockwise or counterclockwise direction. And TE, it is in the clockwise direction. So TE and TL, they are in opposition. Similarly, the force at which this mass M is moving in the forward direction, it is Fe. Whereas, what is the load? It is FL in the opposite direction. So Fe minus FL is equal to M dV dt. This is the linear motion equation. And this particular equation is angular motion equation. So this figure is just given or explored or analyzed in order to give you an idea how translational motion and rotational motion are linked with each other. So what is Te? The electromagnetic torque T is equal to Fe cross product of R. And what is TL? It is FL cross product of R. So what is the angle between this radius and F? It is 90 degree. So FL cross R or Fe cross R, it is FLR sine 90. That means FLR. Sorry, this will be FER and this will be FLR because sine 90 is 1. So this establishes a relation between linear motion and translational motion. Often we can couple two motors so that the load moves in a linear way. So now this is a very beautiful arrangement. So you see, there is a motor which is producing an electromagnetic torque of tau E, and it is connected directly or coupled directly to the first load, which is producing or which is having a load torque of tau L1. So load 1 is having a load torque of tau L1, and the total equivalent moment of inertia of the motor load system, it is J1. So the motor is moving or rotating with a speed of omega m, and it is in this particular direction. So obviously the load will also move in the direction of same direction rather, and the speed is omega m1. And now there is a load 2 whose load torque is tau L2, and it has a moment of inertia of J2. And this load 1 and load 2, they are coupled by a gear. This is one gear and this is another gear. So now our first observation is, if this is the direction of rotation of load 1, then load 2 will move in the opposite direction. This is common physics. Let the number of teeth of the first gear be N1 and the number of teeth of the second gear, it is N2. So A, which is nothing but the teeth ratio, it is equal to N1 by N2. So this is a gear arrangement. So it is a gear arrangement. So now, what will be the equivalent moment of inertia of the system? This is question 1. So A2, or A rather, I have already told you it is N1 by N2. So J equivalent should be equal to J1 plus A2 square into J2. So J equivalent is equal to J1 plus A2 square into J2. And what about the torque? The equivalent torque will be equal to tau, or the equivalent load torque, tau LEQ, that is equal to tau L1 plus A2 into tau L2. So this is the equivalent torque of the system, and this is the equivalent moment of inertia of the system. And you see, this entire figure is simplified to this figure, where this motor is this motor, and this entire system is simplified into this system. So now, when you have reduced this system, it will make your analysis very easy. So now, two things that you will see while analysis. That is, one is transient state, this is number one, and number two is steady state. So suppose you have an electrical machine and the power supply is separated with the machine by a switch. Now you want to turn on the machine. The moment you turn on the switch, so what will happen? There will be some effect in the entire network. There will be some unwanted waveforms, and there will be some desirable or wanted waveforms. So there will be some disturbance in the system. So now some of the waveforms will eventually die out with time. That is known as transient response, and the state of the machine or the drive is known as transient state. And the state of the drive, or the current, voltage, power, or rather you can say the speed, the torque, which is persisting consistently as t tends to infinity, or the time tends to infinity. That means quite a long time. It is known as steady state. The state of the drive is called steady state. So now, an overview of speed torque characteristics of different types of machines are given in this particular figure. So you see synchronous machine. So in synchronous machine, what happens? The rotor speed and the stator speed, they are same. And it is at the speed torque characteristics. As the torque increases, the speed will be constant, only then it will remain synchronous. But yes, you can alter the speed, that is the rotor speed, but for that you have to make the speed of the rotor at all times equal to the speed of the rotating magnetic field. And for that you need a cycloconverter. Now this is the characteristics of, it is given by red, of induction machine. This green line represents the characteristics of a separately shunt DC machine, and this hyperbola, that is the response given by a series machine, a DC series machine. By using power electronic converters, the motor characteristics can be changed at will. This is very important. So that is the importance of power electronics. When you interface power electronic converters with electrical machines, it becomes a flexible electrical drive, and you can change the motor characteristics at your will. This is very important. So now here, if you see the figure, so it is a speed profile and a torque profile. The speed profile is for a particular instant of time or a particular state, and this red line and this blue line is given for another state. So you see the red line is represented when your machine is accelerating. So this is for alpha greater than 0. So if this is alpha greater than 0, this is alpha equal to 0. That means this is a constant speed, area, region. And here if you change the characteristics, so you see the rate of change of acceleration becomes slower, this blue line. So here alpha is so it is also greater than 0 rather. So if this is alpha 1, if this is alpha 2, so alpha 2, that is the acceleration represented by the blue line, should be less than the acceleration represented by the red line, that is alpha 1. So this is nothing but motion control. So you see now, let us analyze the torque which is being obtained corresponding to these speeds at different point of time. So here you see the speed is constant in this particular region. The torque is also constant. Here you see the torque is increasing to 15 Newton meter. It remains constant for 0.01 seconds. And now again its torque falls. So that means you see that the torque is high for a shorter span of time. But for the blue, you see the torque is lower, but this value persists for a larger time. High for a short time and low value for a larger time. So this is how the speed and torque balance is maintained in an electric drive. So I will stop over here. See you in the next lecture. Thank you.